Now let us see the formation of molecular orbitals. The formation of molecular orbitals can be explained by the linear combination of atomic orbitals method. That is the linear LCAO, linear combination of atomic orbitals. We know that an atomic orbital is an electron wave. Therefore, when the waves of two atomic orbitals are combined, there are two possibilities exist. The waves may be in phase or the waves may be out of phase. Suppose psi A and psi B are the wave functions or amplitudes of waves A and B. When they combine, when the waves A and B combine, there are two possibilities. Psi A and B are in phase, that is, it leads to constructive interference. Or when waves A and B are out of phase, then the destructive interference happens. See here, the waves A and B are in phase, that is, they give the waves are in phase means they give signals at highest peak at same time. See here, the waves offset at the same time at the highest peak. Therefore they are said to be in same phase. When these waves are combined, the resultant wave has the amplitude phi is equal to psi A plus psi B. The amplitude of the new wave is more than amplitude of wave A and B. Therefore, in this case, the amplitude of new wave is equal to phi is equal to psi A plus psi B. In the second case, when waves A and B are out of phase, see here in this situation, the waves A and B are in out of phase. See here, it is starting from here, this point, this gives signal at same time, but in one wave it gives signal of crust at this crust. At the same time here it gives trough at the same time. Therefore these waves are out of phase. When these waves are combined, you will get a destructive interference. Therefore the resultant wave is has an amplitude which is smaller than wave A and B. Therefore the amplitude is a summation of psi A. Amplitude is the psi A minus psi B. Here you can see the amplitude is smaller than psi A and psi B. And we know that the probability is given by the square of the amplitude, as in atomic orbitals. Psi is the wave function of the atomic orbital and psi square is the probability of the electron. Finding electron is maximum. Here also, phi square is the probability of finding electron is maximum in molecular orbitals. Okay, so phi square is equal to psi A plus psi B square when waves are in same phase, and phi dash square is equal to psi A minus psi B square. So here it is equal to psi A square plus psi B square plus 2 psi A into psi B. Therefore phi square is greater than psi A square plus psi B square, because you can see phi square is equal to psi A square plus psi B square plus some amount. Therefore phi square is greater than psi A square plus psi B square. So here also phi dash square, here is the amplitude of the probability of the resultant wave when the waves are in destructive interference, where waves are in out of phase, right? Psi A minus psi B square, psi A square plus psi B square minus 2 psi A into psi B. So therefore the phi dash square is lesser than psi A square plus psi B square. Thus, by the combination of two atomic orbitals, two new molecular orbitals form. One by the constructive interference and the other by the destructive interference. The molecular orbital formed by the additive effect, that is constructive interference of the atomic orbitals, is called bonding molecular orbital. And the molecular orbital formed by the destructive interference of the atomic orbital, that is called antibonding molecular orbital. However, the probability of finding electrons in bonding molecular orbital is maximum. So here you can see the probability of finding electrons in bonding molecular orbital is maximum. Probability is maximum here. Right. This is because most of the electron density is located between the nuclei of the bonded atoms. Hence, they interact strongly by both the nuclei. Whereas the probability of finding electrons in antibonding molecular orbital is low. It decreases in antibonding molecular orbital because most of the electron density is located away from the space between the nuclei of the combining atoms. In fact, there is a nodal plane between the two nuclei of the antibonding molecular orbitals, which we'll be discussing later. It is also very important and interesting when we compare the energies of the combining atomic orbitals. The energy of antibonding molecular orbital, is raised by an amount greater than the amount by which the energy of the bonding molecular orbital is lowered. Right, so that is when two atomic orbitals combine, we form two molecular orbital, bonding molecular orbital, antibonding molecular orbital. As we saw earlier, the bonding molecular orbital having a lower energy, greater stability, antibonding molecular orbital, higher energy, less stability. And however, the energy of the antibonding molecular orbital is raised by the amount greater than the amount by which the energy of bonding molecular orbital is lower. The reason for this lies in the fact that in the bonding molecular orbital, the electron density in the internuclear region, that is the region between the nucleus, the electron density in the internuclear region, that is region between the nucleus, is very high. As a result, the nuclei are shielded from each other. Nuclei of combining atoms are shielded from each other. Therefore, the repulsion between the nuclei is very small. Okay, this leads to greater stability and lower energy here. Okay, whereas in antibonding molecular orbital, the electron density in the internuclear region is very low. As a result, the nuclei are nuclei of two combining atoms experience very little shielding. Hence, the repulsion between the nuclei are very large, so that the antibonding molecular orbital is raised much in energy. Then the molecular orbital, bonding molecular orbital is lowered in energy. And here we can conclude the main characteristics of bonding molecular orbitals. The probability of finding electron in the internuclear region of the bonding molecular orbital is greater than the combining atomic orbitals. The electrons present in bonding molecular orbital result in attraction between two atoms. As a result of this attraction, the bonding molecular orbital has lower energy and therefore there is greater stability than that of the combining atomic orbitals. The bonding molecular orbitals are formed by the constructive interference of the atomic orbital, that is additive effect of the atomic orbital. That is when these two atomic orbitals combine, the waves of the atomic orbital combine, the crest fall over this crest, and the crest of the wave fall over the crest of this wave. As a result, the amplitude of the new wave is greater than these two waves. The bonding molecular orbitals are represented by sigma, pi, delta, etc. Similarly, we can also discuss the main characteristics of antibonding molecular orbitals in the wave. The probability of finding electron in the internuclear region is very low in the antibonding molecular orbital. The electrons present in the antibonding molecular orbital result in the repulsion between the two atoms, two combined atoms. And because of the repulsive force, the antibonding molecular orbital has higher energy and lower stability. We can say it does not favor the formation of the bond. That is why we name it as antibonding. The antibonding molecular orbitals formed by the subtractive effect of the atomic orbitals, that is a destructive interference. The crest fall over the trough. Therefore, the amplitude of the new wave is given by phi dash is equal to psi A minus psi B. And the antibonding molecular orbitals represented by sigma star, pi star, delta star, etc.